Okay, so today I want to talk about the longest path problem, and then I will give you an example of the application of the longest path problem called project schedule. Okay, so generally I can say that for any network related problems, it can be formulated by linear programming. And I can tell you, I can summarize that there are two ways to formulate an LP. The first way, so we know that for a network, what are the components? The components are the nodes and the arcs. So these two ways to formulate an LP also focus on the arc and the node. So the first way is that we want arc. We want arc to serve as variables. So I will just write VAR, it means variable. And we want the nodes to be constraints. And the second way is just the opposite. The second way is we want nodes to serve as variables and the arcs to serve as constraints. So I will explain afterwards what does this mean. So first memorize these two ways to formulate an LP. And then let's look at the longest path problem. And I will tell you how to use the first way to formulate an LP in the longest path problem. So longest path problem, let me see. It is like this. So I give you a directed network G, which has node set N and the arc set A. It is a directed network. And so for example, something like this. And also for every arc, it has a weight. Let's say this arc has weight 2, this arc has weight 3, 4, something like this. So this weight can have many meanings, like the cost if you transform some products from this node to this node, or the length, or other meanings. And so suppose now you have some node S and some node T. So the longest path problem, as the name suggests, it means that how can we find the longest path from S to T? So of course we know that this is a directed graph, so it should be a directed path. That's to say, what is the longest directed path from S to T? Okay, so now let us use the first way to formulate an LP on the longest path problem. As I said, the arcs serve as the variable. So can anybody tell me, how can I design our variable with respect to arcs? Let's say for any arc ij in A, what is the corresponding variable? Oh, please. Xij. Xij. So what does Xij mean?
I guess it would mean if it would equal 1 if you use that arc and 0 otherwise.
Okay, very correct. So for any arc ij, in A, we design Xij, which is 0, 1, where 0 means we don't use it and 1 means we use it. So if we want to formulate longest path, this is equivalent to say that on this network for every arc, we should determine whether we use it or not use it. So if we use it, then those arcs should be able to form a path. Okay, that's it. And this is the variable. So what is our objective function? Because we want to we want to maximize the path from S to T. So now suppose we have already found the path. Then no, not already found the path. So now suppose we have already determined the value of xij, whether it's 0 or 1. So how can we design the objective function?
We multiply the distance on our.
Yeah.
Is that so called the distance?
Okay, be careful of your
Okay, yeah.
face mask. Okay, so the objective function is just sigma for any ij in the arc set, Cij times Xij. This is very straightforward. And we would like to maximize this guy. Okay, so now let's look at our constraints. So we want to use our node as a constraint. And what should our constraint satisfy? Our constraint should make sure that what we have found is a directed path from S to T. And what else? Apart from this should be a path from S to T. We should also avoid cycles, right? Because so suppose this is S, this is T. And along this path, suppose you have already found the cycle. And also, to make matters worse, this cycle has a positive cost. Then this problem is not upper bounded. Why? Because you can just go in infinite times along this cycle. Then this problem is not upper bounded. So when we design our constraints, we should also avoid the case of directed cycle. So let's do it one by one. So first, we need to write the constraints corresponds to each node. So how can we formulate the constraints with respect to nodes? Can anybody tell me? Let's say for S. So for S, that's to say, because we want to find a path starting from S. So that's to say, for all the arcs that adjacent to S, say this S has two arcs that come into it and two arcs going out of it. So what should it satisfy?
Should we like assume like the way in should equal to the way out? The value of way should be.
No, this is S.
Okay.
This is the starting point. What should the starting point satisfy? So for example, if we want to go from Baltimore to New York, for those cities that are between them, say Princeton, you get into Princeton for one time, and then you get out of Princeton for one time. But for Baltimore, you just get out without getting in, right? Because you are moving from Baltimore to New York. So that's to say for S, what we want is that you get out for one time and you get in for 0 times, right? So for S, we can write for any Sj in A, the sum of x Sj, this equals to 1. This means out. And also, because we just want to get out of S, so for those arcs that come into S, for an IS in A, xis, this is 0. This means you don't come into S. And how about T? So suppose this is Baltimore, this is New York. You want to come to New York. So that's to say for T, these are the opposite, right? That's to say for any Tj x Tj, this should equal to 0, and for any it in A and x it, this equals to 1. And for all the intermediate nodes, that let's say you go from Baltimore to New York, those cities like Princeton, Philadelphia, for any V such that it is not the start or terminal or the terminal point. We want in equals out equals 1, right? You come and then leave. So I will just omit this. So you should be able to fill this blank in a similar way like that. However, we can write in a more brief way for these constraints. So a brief way to write constraints. So first I need to claim that we write for S, out equals to 1, in equals to 0. For T, out equals to 0, in equals to 1. For the other nodes, in equals out equals 1. This is the most intuitive way. But we have a more brief way to write these constraints. That's to say, sigma j such that Vj in A, x Vj minus sigma I V in A, x IV. So think about this. Here we focus on the node V. All the Vj in A, that's to say for this V. This guy counts those arcs that are going out. And this guy counts the arcs that come in. So what is the difference between them? There should be 3 cases, right? S, T, and for all the nodes that are not S and S or T. So this should equal to 1 if the V is S. This means that for S, out minus in equals to 1. And for T, it should be minus 1 and 0 otherwise. Is that correct? This is a brief way. So let's say for any intermediate nodes that are not S or T. So suppose for this node, there are 2 arcs that come in, and they are also selected, and 2 arcs coming out. Is this possible? So you see that this is some V that is neither S nor J, neither S nor T, and the number of arcs that come in 2, number of arcs coming out 2. So the value is 0. But is this possible? Actually, it is not. So suppose if you backtrack to S, then you must have 2 arcs coming out of S, right? Then the constraints for S is not satisfied because 2 arcs come out of S. Or if you go to T, 2 arcs come in, this is also impossible because what we want is that for S, the number of arcs going out is just 1 rather than 2. So this is impossible. So that's to say, even if you write your constraints like this can also guarantee that this is a path. Oh no guarantee that this is a path, but at least for every node other than S and T, exactly 1 come in, 1 come out. And for S and T, for S, exactly 1 come out, and for T, exactly 1 come in. So this is the constraint with respect to the nodes. So how about the cycle problem? That's to say, how can we avoid directed cycles? Can anybody tell me? Recall what we have learned in traveling salesman problem. So let me help you to review. So in the traveling salesman problem, you also need to avoid directed cycles, right? And how do you determine that there is, apart from a cycle that covers every city? So suppose you want to go to A, B, C, D, E, these 5 cities. And how can you avoid that? Okay, there should not be a cycle between, say, B, C, E. How can you achieve this? What kind of constraint helps you to avoid this? So I'll give you some hint. For any proper subset S of the node, what should we have? To avoid, let me write it up. To avoid cycle. So we want to avoid cycle. What kind of constraint should we consider? You asked me this question in my office hour last night.
Yes. Yeah.
How to avoid a cycle?
We want to make sure. I mean, there is n minus 1 arcs totally.
Whatever. I just want to ask how to avoid a cycle, because now our variable is just xij, whether it can be 0 or 1. That's to say, on this network, for every arc, we have two choices: to choose it or not choose it. But how can we avoid a cycle?
Make sure on each node you has like 1 in and 1 out.
But how about, say, this is Baltimore, this is New York, and you have a cycle Princeton, Pennsylvania, Philadelphia, and say some city in Delaware. This is also a cycle. And in equals out equals 1. And so suppose Baltimore, New York. Does this satisfy this constraint? Yes. But is this a feasible solution? No. So how can you avoid cycle between? Oh, please.
It's like you want the sum of the arcs of, you want the sum of the arcs from the nodes within that subset to be less than or equal to the cardinality of that subset minus 1.
Oh yeah, you are correct. Okay, so that's to say, if you want to avoid cycle, we need to say that for any S, which is a proper subset of the nodes with S not equal to 5, then this ES means that, so suppose among these nodes, I select some of them. And this means that this is an induced subgraph. Let's say you pick out 3 cities between here and New York. And this is the arc set that these 3 cities that they have. Okay. For any ij in ES, that's the arcs in the induced subgraph that caused by S. Xij, this is less than or equal to S minus 1. Because why does this make sense? This makes sense because, so suppose you have selected 3 cities that are intermediate to Baltimore and New York. And if they want to form a cycle, they should at least use 3 arcs. That's to say, if you want to select a proper subset from the nodes, if you want to formulate a cycle, then you need at least this many arcs to form a cycle. Does that make sense?
What does S mean? Is S means like the nodes, the number of nodes?
You mean absolute value?
Yep.
Cardinality of a set.
Oh.
Right. So I think you should have already learned this in real analysis. Right. So the cardinality of this. So suppose S is Boston, New York, Baltimore, then S, the cardinality is 3. Number of elements in it. Okay, so these are our constraints. First, we want to make sure these constraints make sure that for the cities, for those intermediate ones, come in for 1 time, come out for 1 time. For the start, just come out. For the termination point, just come in. And this helps us to avoid cycle. So this is the formulation of the linear programming for the longest path problem. Can anybody tell me if there is any problem with it in terms of the implementation? What's if I want you to find the longest path problem in practical, is this a practical way to solve the longest path problem? Actually, I don't think so. Although in this course, you just need to know how to form a linear programming problem. That might be enough if you just want to take the exam and get a good grade. Because in the exam, there will be many problems that ask you, okay, so please formulate a linear programming. However, this indeed is not possible. Why? Because we want to find a proper subset of all the nodes. What is the number of proper subsets of a set? Sean, can you tell me? What is the number of subsets of a set? Let's say we have a set N, and it has cardinality N, how do you pronounce it? Let's say 10. How many subsets does this guy has? Yeah, 2 to the power of 10. So that's to say, if you want to find all the proper subsets, that's to say you have an exponential number of constraints, which indeed is very intractable if you have too many number of cities. So we'll talk about this problem later if we have time after we finish today's section. So I can talk about a more practical way to do it. So I will erase this. But don't worry, in the exam, you will just be asked to formulate the linear programming. Whether it has an exponential number of constraints, does not matter at all. Okay. So next, I want to introduce the second way to formulate a linear programming problem. That's to say, we use the node to serve as the variable and the arc to serve as the constraint. So before I introduce this way to formulate a linear programming, I want to give you an example. This example is also a longest path problem example. And using this example, you will know why do we have this class of problem, the longest path problem. So let's see an example. So the example is called project scheduling. So we have several tasks. We have several tasks, say A, B, C. We have these tasks, and some of them should be done sequentially. And some of them can be done simultaneously. I have omitted some words here. So let me explain. So you have several tasks, say A, B, C, D, E, F, G, blah, blah, blah. And some of them, they should be done sequentially. This is just like, say you take courses in university, you have prerequisites. You cannot say you take an advanced level course without taking the prerequisite. But some of them can be done simultaneously. Let's say you can take linear algebra and calc 3 simultaneously. It doesn't matter at all. So these are the tasks. Let me give you an example. So suppose you have project A. Oh no, I think that this is too small. So these are the projects, and these are the prerequisites. I don't know if I spell correctly, but never mind. This means prerequisites, and this means time to do it. This means that for this project, how much time do you need to complete it? This is just like, say, in a university, for a course, a normal course, it takes 1 semester. But if it is a thesis, it may take a year long or so. And for some courses, say in Bloomberg School of Public Health, their courses are quarter-based. So you just need a quarter to complete it. Okay. So suppose we have A, B, C, D, E, and F. These are our projects, or say our courses. A and B does not have prerequisites, and you need six hours, 9 hours to complete A and B. And for project C, you need prerequisite A, B. And for project D, you also need prerequisite A, B. And for E, you need D as a prerequisite. And F, you need C and E. This is just an example. So you can feel free to copy it. So let me complete the numbers. Okay, so these are the first column is the project. The second column is the prerequisites of this project. And the third column is the time to complete this project. Then the way that we tackle this problem, So the project scheduling asks us the question, what is the minimum time that is required to complete all of them? This is just like, say, I give you the course list, and some of them are prerequisites, some of them you can take just together. What is the minimum time for you to graduate? So this is the core idea of project scheduling. And the way that we tackle it in this course is to use a network to represent it. We use a network to represent. So first, we create 2 nodes, which are start and finish. This means your first day of university. This is the day that you graduate. And because we have these many projects, the way we do it is to create these nodes. Say we have A, B, C, D, E, F. These are the tasks that we want to do. So then we see that here are prerequisites. So what does this mean? What does this mean in a network? How can we explain the relationship of prerequisite? Can anybody tell me your idea?
But an arc from the prerequisite to the course that it's a prerequisite for.
Yeah, very correct. So we see that project C, it has prerequisite A, B. So that's to say, we use these 2 arcs pointing from A to C, B to C. These are the prerequisites. So let me complete. So D requires A, B as prerequisite. F requires C. And F also requires E. And E requires D. And then, because we from this plot, we see that from F, you also need to finish. And for start. So actually, I can also tell you that in the project scheduling, if you just disregard these arcs. So for first, please ignore this start and finish. Just look at A, B, C, D, E, F. What's the property of this directed graph? Let me give you some hint. Does it have cycle? No. So actually, in project scheduling, we are dealing with something called DAG, directed acyclic graph. Acyclic means that there's no cycle. This makes sense, right? So for example, when you take courses, you cannot say that you take course A, and then course B, and then course C. But course C is the prerequisite of course A. This is impossible. So in reality, DAG, directed acyclic graph, this really makes sense. Okay, so let me this. All right, so this is our graph, and we know that if you want to do A, you don't need to, from start to A, you have no cost. You can just start with A and B directly, right? But we know that A, for project A, you need 6 hours to complete it. So let's say from A to C, and from A to D, 6. So the weight of the arc in this network means that the cost that you need to complete this task. Say A, you need 6 hours, B, you need 9 hours, and C, you need 8 hours, D, you need 7 hours, and E, you need 10 hours, F, you need 12 hours, right? So now we have already found the weight to this graph. Okay, so now let's try to formulate this linear programming using the second idea. We set the node as the variable and the arc as the constraint. Let me write for any node J from A to E, and also start and finish. We set a variable Tj. Anyone has an idea what does Tj mean here? Remember that now our nodes are the variable. So what does Tj mean? Remember that in this task we want to minimize the time that we complete A, B, C, D, E, F. So what does Tj mean? To complete or to start. Yeah. So we actually but you are correct. Actually, we can use Tj to represent the time to complete it. But for any task, how to say, commonly we focus on the time to start it, right? Let's say you take this course. We always say at the beginning of some semester, rather than we complete this course at the end of some semester. This is just a tradition. So Tj means that the time to start task J. This is the time to start task J. And also because J means A, B, C, D, E, start, finish. So we also set a DI. This means that the duration of DJ, the duration of task J. So this is a constant. DJ is a constant, the duration of task J, which is given. But for TJ, the time to start task J, this is what we need to determine, right? So what are we minimizing now? We are minimizing what? We minimize the total time that we need to complete A, B, C, D, E, F. So what is the objective function? This is the objective function. We want to minimize what? What are we minimizing? So remember J, we have A, B, C, D, E, start, finish. And TJ means the time to start task J. And also finish, for start and finish, means that the time to finish, the time to start. So what are we minimizing?
The duration.
Well, yeah, what is the duration? Use the random variable to tell me.
Oh, it's like we can use the finish time to minus the start time.
Yes, correct. So it means that T finish minus T start. What are the constraints? What are the constraints? The constraints, let me tell you directly. So the constraints means that look at any arc in this network, say C and F. That's to say the start time of task F must be at least the start time of J plus 8, right? This is the earliest time that we can start task F because task F has prerequisite C. You need to start C and complete it in 8 hours, and then you can start F. So this is the earliest time of F. So the constraint is that such that Tj minus Ti, this is greater than or equal to Di for any ij in a network. That's to say, I is the prerequisite of J if ij is in the network. And the start time of task J is greater than or equal to the start time of task I, plus the time that you need to complete the task I. So this is the constraint. So then we have finished, because you see the nodes are the variable and the arcs are the constraint, right? You see it here. This constraint is formulated by the arc ij. So that's the way to formulate a linear programming with the nodes as the variable and the arc as the constraint. And I can also say that I can also tell you that these two guys are dual to each other. That's to say, here you minimize here is equivalent to maximize here. So my next question is, for this project scheduling, how can we formulate the linear programming with the first way? We set the arc as the variable and the nodes as the constraints. Can anybody just briefly tell me how can we do this? We use the first way to formulate this linear programming. So remember that in the first way to formulate the linear programming in the longest path problem, we are maximizing something. So because I tell you that the first way and second way, they are dual to each other. In the second way, you are minimizing. So in the dual problem, you should maximize something. And I also tell you that in the first way to formulate a linear programming, you use the arc as the variable. Let's say CF, this is the arc CF, and we want the nodes to serve as constraints. This might be a little bit hard to think, so I can tell you that I can just tell you. So this problem actually it is also finding the longest path. But why does finding the longest path from start to finish? But why does this make sense? This means that as long as you can find the longest path from the start to the finish, this is the minimum time that is required for you to complete these tasks. Think about it, why? You find the longest path. And along this path, because this is a directed network, you find a longest directed path. For all the nodes, for all the intermediate nodes on this path, they are prerequisites to each other, right? So if you find the longest path from start to finish, this is equivalent to the minimum time that is required to complete all these tasks. Please.
So just a clarification. So when it's like when A, B is a prerequisite for C, does that mean either A or B needs to be taken before C, or both A and B?
Both A, B.
Both.
Yeah. So for example, for combinatorial optimization, if you want to take combinatorial optimization, you should have already learned linear algebra and discrete mathematics. You should learn both of them. Right. So you just understand this in a way that you take courses in university. So think about it. If I find the longest path in this network, then for other paths from the start to finish, they have length less than this longest path, right? And within this time, you can also complete this. But these longest paths, they set the minimum time to complete all of these tasks. You understand this?
Yes, okay.
Okay. For you, it makes sense. How about you guys?
I have a question about this graph.
Okay.
If the prerequisite was like 2 classes, if we need to get the class C, we need A and B. So like
A, B can be done simultaneously.
okay, so from start to A and start to B, I can define it as just one path.
From start to, because A, B, we know that they are the beginning of this network. So I see that we have some time. I can talk about the graph's topological ordering to you. So we see that you can start with any one of A, B, right? So that's to say, this is the beginning day. This is the first day of your university, and you can do say calc 1 and linear algebra 1 together. And there's no cost to start.
Okay.
Yeah. Okay. So I spent the last several minutes to talk about topological ordering. Actually, I've not prepared this content yet, so I'll just talk to you with what I understand. So the topological ordering, what does this mean? Is that clear? Seems that it has run out of ink.
I can see it.
Oh, how about? Excuse me, what's your name?
Thomas.
What?
Thomas.
Thomas. Okay. So is this clear for you?
Yeah.
Okay. So topological ordering. No worry, there's nothing related to topology in pure math. So topological ordering, when we say topological ordering, it means we are talking about DAG, directly acyclic graph. So topological ordering means, so suppose you have some network, like you see there's no cycle, no directing cycle here, right? So topological ordering means that so here you see there are 4 nodes. So you place your 4 nodes in a line. And then in a topological ordering, it should satisfy that there's only arc going from a left node to a right node, but there's no arc going from a right node to the left node. So in this, if we say A, B, C, D, how can we organize this into, how can we put A, B, C, D in a line? And then we only allow the arcs to come from a left node to a right node. But there's no arc coming from a right node to a left node. So it seems that we can put D in the beginning because there's no arc going to D. And we can also put A here, but we can also switch A and D. We put A here and D here. No worry, because there's no arc going to A or going to D, right? So let's say we put D here and A here, and we put B here, C here. Then we add the arc. So we have an arc going from D to C. And we have an arc going from A to B. And we have an arc going from B to C. And we also have an arc going from A to C. So you see that now if we order the nodes in this DAG in this way, D, A, B, C, or actually you can do it in A, D, B, C. You can switch these 2 bytes. It doesn't matter. So if we order these nodes in this way, then the arcs only go from a left node to a right node, but there's no arc going from a right node to a left node. Why does the topological ordering make? Why is the topological ordering important? Actually, if you look back to this graph, the nodes with the higher order in the topological ordering means those lower level courses, right? Because if you say you study science or engineering, everyone must take calc 1, 2, 3 and linear algebra at the very beginning, and they have no prerequisite. So in a topological ordering of a DAG, for those nodes that appear earlier, it means those lower level courses, say 100 level, 200 level courses. And along this line, you go from the nodes with a lower ordering to a higher ordering. You actually go to more advanced level courses. So that's the reason why topological ordering is quite important. But I think in this course, you will learn topological ordering later on. So I will not go into too much details about it, but here I emphasize topological ordering just to tell you that the reason why we add the start and finish node, and then we just use the start to point to AB rather than use the start to point to C. Why don't we point from start to C? Because C does not have the lowest topological ordering, but AB has. A has, you can, if you ignore this, just look at those 6 nodes in the 6 intermediate nodes. Then if you draw a topological ordering, you can put A at first, B at the second, or B at first, A at the second. Doesn't matter at all. So that's the reason why when we construct this network for the project scheduling problem, after you add the start and finish node, we only point from start to A and start to B because they have the highest topological ordering. And the reason why we only point from F to finish rather than from C to finish, from D to finish. Can you do that? No. Why? Because after C and D in topological order, you have nodes that are behind them. So F has the highest topological ordering. So that's the reason why we just point from F to finish. So this is like 100 level courses, 200 level courses, 300 level courses, and 400 level courses. And then you graduate, right? But make sure that you pass all of them. Otherwise, you fail and you will not get your degree. Okay, so I think we can just stop here. No worry about topological ordering. I think Dr. Costello will talk about it. If she does not talk about it, I can tell you how to find topological ordering later on. Okay, that's the end.